We have a special seminar. We have a guest from Broadcom Bulgaria, as well as from Cadence. This is a special occasion because these two companies are actually building bridges between science and highest contemporary technologies. So to introduce our guest, I would like to ask Associate Professor Manova to introduce our guest and to manage the seminar.
Thank you very much. Our seminar will start with Mr. Nikolai Bochet from Broadcom, Bulgaria, who will give a lecture about Broadcom at a glance.
Yeah, good day, everyone. My name is Nikolai Bocев. I'm an IC design engineer in Broadcom, Bulgaria. And I'll briefly talk over the history of Broadcom Inc. And as you may already know, it is an American multinational company that is designing, developing, and supplying a wide range of semiconductor and also software for a very diverse set of industries. And I'll walk you and let's go together to see what makes Broadcom so special. So in the first slide here, I've covered that our company is diversified in both semiconductor and infrastructure software. It's built on engineering experience, and we have access to the latest technology in the field, and have been driving innovation for the past 50 years. So our portfolio is including multiple applications within these four primary markets: the wired infrastructure, the wireless communications, and enterprise storage, and also industrial. And other than this, it's including the data center, networking, enterprise software, and also storage, broadband, wireless communications. And over this lecture, I'll go through most of these fields and cover it more. But first, to take a glance at the company that we have today. So on this slide, you can see the FY22 net revenue of the company is nearly $33 billion with a very high gross margin of about 75%, which is very high. The company is using all the latest and greatest technology of the modern world, and investing nearly $5 billion each year on research and development. And there is a significant number of patents that the company is holding, making it a really big leader in this field. We're competing with the best ones in the field, NVIDIA, and even as of now, I think that the market capitalization of the company is bigger than the one of Intel. And this is not this is happening as a part of a series of very strategic acquisitions that have happened over the years. Over here, you can see the company was founded in 1961 as a part of HP Associates. It is the semiconductor part of Hewlett-Packard. And back then, until 2016, the name of the company was Avago Technologies. It was specializing in the early years, mainly in IC design, integrated circuits, application-specific integrated circuits, system on a chip, and other specialized components in the field. And some of the latest acquisitions, especially the ones of Brocade, CA Technology, and Symantec has made the company a leader in the development of software solutions. So after 2016, Avago Technologies is merging with Broadcom Corporation to form the Broadcom Inc. company that I'm representing now. And ever since then, the company has started working more and more in the software, covering the enterprise class of software solutions. You can see some snapshot here of the net revenue of the company ever since this merge that happened, and this is where we are now divided into the different segments. 1/4 of the revenue of the company is coming from software. The other is through semiconductor solutions. And the need for faster and more reliable internet traffic is growing year after year. Here you can see that this is just an illustration. In 2021, the estimated traffic of the internet traffic, it's more than 3 zettabytes. That is a really significant number, like unimaginably big. So Broadcom is trying to cover everything that needs to be improved in social networking, cloud computing, video processing, to fulfill the need for such a huge amount of data that we use on a day-to-day basis. Broadcom Bulgaria is mostly taking part in this networking high performance connectivity solutions. We are working on devices that are known for their speed, reliability, and scalability. It's providing solutions for the enterprise, hyperscale data centers, and switching, routing, physical layers, and coherent chips, and optical interconnects. Here, also I can cover the server and storage solutions that we have. It is one of the most of the world's largest cloud providers, search engines, data center operators are using solutions that are done by Broadcom. In the broadband, also Broadcom is providing solutions to providing the internet, the high-speed internet, TV, voice services from the service providers to the end customers. We include set-top boxes, including DSL models and other broadband components. In the wireless, we are famous for Wi-Fi, Bluetooth, and GPS chips that are going into the latest smartphones, tablets, and laptops. Our touchscreen controllers are in one of the latest devices on the market, inductive charging, and also different kinds of optical sensors in the area. So it's like we're bringing all the latest technology from the data centers to reaching until here to the end customers and these smart devices that are in your back pocket. Apart from that, Broadcom is known for is providing different solutions for the industrial, like industrial control systems, smart metering for the industry, and other industrial applications. So that is about Broadcom as a general. I'll spend more time. I forgot the software part of it. In the software, we are providing latest years the enterprise class solutions for for the big companies using a combination of DevOps, Value Ops, AI Ops. We help the business to optimize processes, prioritize and achieve better results with in less time. And on top of this, we have the cybersecurity, identity management solutions, and payment security. This is all coming from Semantic and so on. Here, okay, going to Broadcom Bulgaria, focusing more on our offices in Bulgaria. This is actually a slide from the presentation of our CEO, Hoktan. And he shared that, and you can see our Plovdiv office is on the map. This is one of our biggest offices there, and I wanted to share this with you. Broadcom Bulgaria was established in 2017. It's based on ASIC Depot Design Center that was done 15 years ago, and has been with a strong connection with the Broadcom Corporation ever since. We have more than 215 engineers as of now in Sofia, Plovdiv, and Varna offices. We have a very low attrition rates, about 3 to 5%, which basically means that our engineers are staying for longer and staying with the company for a longer time comparing to the industry. The company is an important part of the IT industry because we are a real data center inside in Bulgaria, and we have the latest, really the latest technology. We're working on the most of the biggest design centers in California, also India, Israel, and we're taking part in some in the chips of the future actually, and working on most advanced nodes like 5 nanometer, 3 nanometer also. And in terms of, we can say that in terms of innovations and really the possibility to have the latest technology, we're one of the best companies in Bulgaria. We're very proud to say that probably every time you post a thread, email, etc., there is a big chance that you're already using some of the solutions of Broadcom that we in Bulgaria have participated in the development. But the company is trying to have a very good relationship with leading universities here, and this is a part from why I'm here, opening the Digital Design Lab and in Sofia University. This lab was possible because of the collaboration between the Faculty of Physics, Broadcom, and Kazan Design Systems. Special thanks, by the way, to Denica, that she was not able to join us today, but she had a really good connection with the Faculty of Physics to be able to be here, and probably will continue this through series of next courses in the years. So at the moment, I can comment about the available positions in our company. I can say that we have a very thorough and intensive training that is led by very experienced engineers. The main areas that we're covering are design verification, which is basically testing building a full testing environment for the RTL code written in Verilog or VHDL, and making sure that the design is doing everything according to the specifications and so on. This is actually in one sentence. This is the QA for hardware design. The physical design position that we have is the next step in the circuit design. It is ensuring that this already verified RTL can be transferred to GDS and become a real integrated circuit, meeting all the design rules and technology nodes, and so on. This is actually what will be what will be doing the students in the digital design lab, using the cadence systems and exercising on backend digital design. And we have a few software development positions in the company. The software designer's goal is to create the interface and allow the end user to use the full range of the hardware capabilities. Once the chip is ready, and be able to use the chip in the C programming language, to be able to read the registers inside and so on, and control input outputs and so on. In the QA responsibilities, they are responsible to test all these different applications that are already done and ensure everything is working and there are no issues reported. And in the end, we have the DevOps that is mainly focused on automation of the software and communicating to make the better series of tests and different APIs that are required. That's about it from my presentation. Thank you so much. And if you have any questions, I'll try to answer any of them.
Thank you very much. Are there any questions from the room?
Yep, thank you. When you hire new people, what are the main deficiencies you see in their skill and knowledge? Because certainly you need to educate additionally them, I mean, to train at least for the specific things, but what you think that is generally not well known, and it should be from the university, for example?
I can't tell for sure, but we have very talented engineers coming out of university. I think that the main thing is the desire to learn. This is one of the main requirements, because it's kind of all these positions that I'm sharing here are very specific, and other than these similar courses that we are doing in this digital design lab, there are not many places that you can get a feel of the real field. So in general, I think it should be a general idea of electronics, and also the VHDL, so on, but nothing is really a requirement that I can say that it's missing. Like our education system is good enough, but the people need to be ready to learn more about the real specifics of the work that needs to be done. Logical thinking is also one of the main components. Rennie maybe can comment also on that, but this is one of in the initial steps of the training, the people are put under pressure to see if they have the analytical thinking and can implement the newly learned things. That's as much as I can answer your question. I know.
Already a tough question.
Yeah.
How you motivate people?
Yes, very.
With great mentors and guide through the whole process, and even after the training, we still have great mentors that are part of the different teams that we have. So with the management and the great environment that we try to provide. We actually have very successful candidates from electronics, from the different faculties and majors, and as long as candidates are very determined and they want to succeed and they want to be able to climb the ladder in hierarchy, and we try to provide as much as we can on our side. But at the end of the day, what is most important is to have this logical way of thinking, to be smart, and really to be motivated to learn, because everything else you can receive from our side.
Okay, the Mexican hack is one of the most widely used way. That's how it became your logo.
Oh.
It is not the Mexican hack.
Yes. A waveline, but the waveform, but I'm not really sure I know the history of that. As far as I know, it's going back from Broadcom Corporation back in 50 years, 60, something like this. So I'm not really aware what is the reason for that.
Questions. The first one is you have mentioned an impressive number of patents you own. Is the Bulgarian office of Broadcom involved in this sort of research and development which leads for patents? And if yes, to what extent you are open for collaboration with the universities in this field?
Not sure how I can answer. I'm not aware. Usually we are involved in multiple different projects around the globe, but don't know the exact way the patent acquiring is done. So maybe we can get back to you with an answer to this question, because I cannot answer right now.
And my second question is more or less related on gossips. We have heard in the media that Broadcom is about to acquire or merge with VMware.
Yeah.
So what is it exactly? Are you acquiring VMware or you're merging with
Acquire. I think you're.
And, what is the, I would say, what do you expect out of this action?
The idea, I believe, is to acquire VMware if the European Union allows this acquisition. And the idea and the company's strategy is to acquire more and more software companies to extend this market. So because we are already a big leader in the semiconductor field, and I think that the general company plan is to acquire more positions in the software.
The deal is almost done. We're still waiting for the final level and allowance of the European Union, but we probably will be acquiring manufacturing margin, because we are the bigger company and the deal is for more than $61 billion. One of the biggest deals actually in the industry for the past few years. But everything else is just speculations at this moment, so we can't really talk more about that.
Thank you very much. Are there any other questions? Professor Bocef?
Curiosity, you mentioned a big data center. Do you build your own or use
I think we built chips for data centers. Like yes, we have solutions for every part of that field. But in going into specifics, I can't answer your question. Thanks.
Other questions? Are there online questions?
Okay, thank you very much. Thank you. Yes, of course. Sure. I hope so. You have to switch. I can just, but this is the share screen. Okay. Oh, okay, now it works. But now you have to share again. Okay. So. Oh, okay. Okay. Online you can also hear me. So can anyone type something?
Yes, we do hear you.
Okay, great. Good. So good afternoon, everyone. So thank you for inviting me. So actually now it's for the second time here at the University of Sofia. So I can do this the presentation. And so today we are going to talk about AI. So AI in general, and AI also how it's applicable in EDA, so in electronic design automation. So for the ones who don't know me, so I'm a University Program Director at Cadence Design Systems. So Cadence Design Systems, it's an American company, and our business is providing electronic design automation tools. So these tools you need in order to develop semiconductors. So like, for example, Broadcom. So we're using a lot of our software in order to design all the products which Nikolai has mentioned in his previous presentation.
And so you can imagine that these products are very complex, and so the chips that drive these products are also getting very complex. And in order to manage the complexity, so now AI is going to help the engineers to create these circuits. So okay, so we have some technical problems, but maybe can you just forward the slides? So we have some technical difficulties. Yeah. So, so no lecture about semiconductors can be done without mentioning Moore's law. So as you all know, so this law is driving the whole industry. So the idea of the Moore's law is that the complexity of a chip doubles every 18 months. And now there are basically two different directions. So one is called Moore. So that means that this progress of doubling of the complexity is still ongoing. And the other direction is so-called modern Moore. So these are developments how to make the chips more complex, but without doubling the amount of transistors. So now I'm going to explain so what actually means. So next slide, please. Or can I try? No, that doesn't work. Yeah, okay. So first, let's talk about Moore. So currently we are at the technology node of 3 to 5 nanometers. So 3 to 5 nanometer, this means this is the length of the gate of the transistor. And so why it's still beneficial to go to the next technology node? It's because you either get better performance. So compared to 7 nanometer nodes, so you get 15% better performance for the same power consumption compared to 7 nanometers. So on this is for 5 nanometers, and if you go to the 3 nanometers, so then you have another 10 to 15% better performance. Or you can do power savings, so you're consuming less energy. So for example, it's important for your mobile devices. And then you get 30% dynamic power saving for 5 nanometer compared to 7 nanometer, or another 25 to 30% from 5 nanometer to 3 nanometer. And additionally, you get increased density, so you can squeeze more transistors on a certain area size. So here you have 1.8 density compared to from 7 to 5, and another 1.7 compared from 5 to 3. So there's a certain benefit just to continuing squeezing the transistors. But this comes at a price, and so the first price you can see here. So it's even mentioned in dollars. So in the past it was quite simple. So the price per transistor was always reducing when you switch from one node to the other node. So that basically means that, for example, you have a processor and 65 nanometer, and you want to add a second core to this processor. So then you just switch to the next node, and then these additional transistors for the second core, they come basically for free, because the transistors are getting cheaper at the next node. But this is no longer the case. So starting from 28 nanometers, the manufacturing costs are increasing. That means that now you don't get this free lunch with the transistors, but now if you want to add from 32 cores to 64 cores, so then the price for the processor is basically doubling. So you don't get this saving anymore. Also, so one of the reasons why the manufacturing is getting expensive is because the most important step for the manufacturing is so-called lithography step. So this is where you have a mask, and then you have a light source, and then with this light source, so the light beam is going through the masks and leaves a pattern on the silicium wafer. And so far you could use the wavelength of 193 nanometers, but now this wavelength is too big. So in order to do all these fine patterns on the silicon wafer, so therefore you have to switch to extreme ultraviolet wavelengths, so which is 13 nanometers. But this is extremely expensive because this light is not reflected by mirrors. It must be in a complete vacuum. So the machinery in order for this lithography step is getting very, very expensive. And therefore, the manufacturing costs are going up. Then another problem is that while you can still scale for digital, so for the standard cells, you can no longer scale for analog or for SRAMs. So now on a chip, so on a regular SoC, the SRAMs and the analog parts are the biggest part of the chip. So now you can only scale digital parts, which is the smallest part. So therefore, you don't really get the benefit of scaling, because most of the parts are not scalable. Then there's a problem with the local variation. So here you can imagine that when now a beam goes through the mask, so then we are starting counting photons. So how many photons are falling on a certain part of the silicon wafer. So if there are not 10 photons, but 15 photons, so you already have a variation on your chip. So therefore, this is something you have to take into account. Then there is also a lot of DRC rules. So you have to check different geometries. There are a lot of parasitic effects. So there are capacitance, there's resistivity, so which you all have to take into account, which you have to simulate, and this all drives the design costs up. So here are some statistics. So in order to design a chip in 28 nanometers, so you had to expend $30 million, and now for a 7 nanometer SoC, so these are 271 million. So that means that you also have to find a right market, so where you can sell your chip, so that you get back the costs which you spend it for the development, and so therefore you have to address huge markets with your products. But what is quite interesting is that so this is this other graph. No. Can you just go? Yeah. So this graph basically shows you. So HVM stands for high volume manufacturing. So it means how long does it take till from the production start, so at the manufacturer, like for example TSMC, till you get a big number of wafers in a certain technology. And what is interesting is that so if you look at N5, so N5 is the 5 nanometer technology, that it's the fastest ramp up ever. So that you get into a high volume manufacturing for 5 nanometer technology faster than with 7 nanometer or 16 nanometer. So that means that the products for 5 nanometers are still very, very demanded, because TSMC needs to produce all these wafers and then provide it to the customers. And this is also something which is very historically unique, because usually in the history, if you have something new, so some new technology, so usually it's rarely available, it's very expensive, it's available only through military or through some very rich people. But now we see that very, very advanced technology, 5 nanometers, so very, very complex, but it's immediately available basically through every one of us. So here your latest mobile phone, which you can go and buy for $1,000, it already contains the chips which are created in 5 nanometer technology. So this is something, this is quite historically unique. So next slide, please. Oh. Yes. Yeah, but the problem with Moore's law is that so because of these restrictions which I have explained before, so the increasing costs, so therefore also the scaling is not as fast as it was before. So there are not too many options what can be optimized. So you can see that the clock frequency is flat, so already for a decade. Also how you can optimize the device, the transistor, so you also get at a certain border. So the only parameter which is still scalable is the system energy efficient performance. So that means that now you have to optimize the whole system, how it behaves, so how much power it dissipates, and by optimizing this parameter, you can still get more efficient and more powerful systems. And this is something now we get into more than Moore. So more than Moore is basically optimization not on the transistor level, but optimization on the system level. So how does it work? So optimization on system level. So one way is to disaggregate the whole system. So in the past, everything was squeezed on one SoC, so on one system on a chip. So this is the way how to save costs. So just through what was before a PCB. So now everything is in one chip. But now with the problem with the scaling problem. So the idea is so let's have different wafers and combine these wafers together. So with some clever packaging. So if you cannot scale SRAMs, or if you cannot scale analog, so then let's manufacture analog and memories on a different wafer in a different process, and then put them together with the digital part, which is still scalable, and put them together on a different wafer and not on the same wafer. Or if you have some other technology, like for example silicon photonics, or you have MEMS devices, or if you have gallium arsenide or gallium nitride, so then let's do some clever way of packaging and then put everything into one system, but not on the same wafer. And so therefore now there are many different new ways of packaging have been created, and this is also something that needs to be taught at universities, because so far packaging is not a topic which is very popular at universities, but this is something that will definitely be more and more in common. So here are different ways of how to package a chip. So here we have the system in package. So this is where you basically have different chips which are stacked on each other. So then you have then you can put two wafers, one on each other. So then you can put several wafers on one on each other, and use so-called through silicon vias in order to connect these wafers. And then so the ultimum is basically transistor stacking. So then you don't have two-dimensional transistors anymore, but you have three-dimensional transistors. So for example, an N transistor, and on the top there's the P transistor. So this is the most efficient way, so how to package transistors together. And so here you see what is the advantage of this. So this is the pitch scaling. And so the interconnect, so how close are the pins from one from each other. So here, when you are in the package staking, so you are 1 millimeter to 400 micrometers, and here you are on a scale of 100 nanometers. So the interconnect between the different devices or different wafers. So what you see here, so it's not available yet, or at least it's available in the labs, but not it's in production yet. So what you see here are basically 2 wafers, which are packed face to face. So basically like this. So here you see the bonding pads between these 2 wafers. So here you have the substrate of one wafer, substrate of the second wafer, and so they are put together. And additionally, you have so-called backside. So that means that there are also electrical connections. So backside PDN. So PDN is power delivery network. So this way, so the whole power connections and power distributions are on the backside of the substrate. And then you have the TSVs, so the through silicon vias, so which are connecting the backside. So this is how it works. So this connects the backside with the front side. Must be really careful here. So now you can imagine that in order to create such a system, so there are a lot of constraints. So, for example, now that you see there's a signal, so which is going from the one transistor, then goes through the whole bonding pads, then goes through the silicon via, goes to the external connection. So, of course, there are a lot of signal integrity questions, a lot of power thermal questions, a lot of parasitics. So all of this has to be taken into account to ensure that all the signals on this chip are so they are not disturbing each other. So they're still strong enough to get to the outside pins. So all of this has to be simulated. All of this has to be verified. You have different databases. So this is a big engineering task. So to create such a system. So therefore, so Cadence has created a platform which we call Integrity, and in this Integrity platform, so you have different simulators, different checkers, different engines. So you have, for example, an engine for thermal simulation, for power simulation, for timing simulation, for physical verification, and then these engines, they are accessing one database. So in this database, you have the data of all wafers, of all designs, of all the interconnections between these wafers, and then you can start checking if signal integrity is fine, if the power delivery is fine, timing, and so on. So this integrity tool is designed in order to be able to create such systems as I showed before. So now let's come to the trends in machine learning. So now we have learned all this modern Moore. So why how is it connected to machine learning? So for the N5 technology, the question is where are these chips needed? So why do you need to develop this N5 technology? Where are the chips going? So here we see networking. So this is Broadcom. So is it now a secret if I tell that you are also working on 5 nanometers? Okay, so now I told the secret. Good, but so you see also CPU, GPU. So this is something. So this is the processor for your iPhone. So here, no, sorry, GPU, CPU. This is something for example NVIDIA or AMD for their GPU, CPU. So you have here the smartphone, but you also see a big portion goes into AI. So these are the processors which are specialized on AI operations. So why is it necessary to create specialized hardware for AI? This is because the models for the AI are getting bigger and bigger. So in the past, so you have to create a model for for example a language model or a picture model or a video model, a video audio model, so which the AI can work on. And the size of these models in the 60s till 2000, it was kind of similar with the progress of the Moore's law. So basically the Moore's law is doubling every 2 years, and the complexity of the models is also doubling every 2 years. So therefore the available hardware was able to keep up with the complexity of the models to process it. But now with the explosion of AI applications, the size of the models also exploded. So basically we have the trend now that AI models are doubling in size every 3 months. So we are much faster than Moore's law. So that means that now we have to find ways so how to create a hardware which is able to process these models, but at much higher speed than the Moore's law. So here we have to look at the system optimization in order to get this required speed. And exactly this is something that happens. So you see here different companies, they are creating AI accelerators. So for example, NVIDIA has created DGX A100. So these are their AI accelerators, but they are packaged in a very dense way. So with very advanced cooling. So in order to create as dense platform as possible. Or we have Tesla Dojo. So this is also a supercomputer for AI applications, and it contains thousands and thousands of cores, which are also the very advanced cooling and very advanced power delivering. But this is optimization at system level in order to create a powerful computer which is powerful enough to process the latest models. So then we have also the Google TPU. But so from my point of view, the most interesting one is the Cerebras. So basically what they do, so there's a wafer, and then they just make it square. So they saw the round parts, and then they do the interconnect on the wafer. And so then you get basically this is a chip. So this is a chip which is certainly the biggest chip in the world. And on this chip you have in the first generation there are 400,000 optimized AI cores, and in the second generation in 7 nanometer you have 850,000 AI cores, so which are on a single chip. Of course, this is they need a lot of cooling, a lot of tricks so how to deliver enough power. So these are kilowatts of power that are driving this chip. But so now if you see, so there are 2.6 trillion transistors, and these 2.6 trillion transistors, it's roughly similar to the amount of synapses in the human brain. So here we are now at the complexity of human brain in such a device. But as you can see, so the human brain consumes around 20 watt, while this thing is still consuming kilowatts. So you see how efficient the human brain is compared to this, and so how much work still needs to be done in order to match electronics with human brain. So now the question is, so what are we going to do with all this AI? So where are we going to? So what is the aim? And here we have So Hans Moravec, he is a philosopher, and he created, he calls it landscape of human competence. So what does it mean? So you see that here it's an island, and on the island there are mountains. And on this mountain, and every peak of the mountain is a certain human competence. So for example, the ability to translate from one language to the other, or to create music, or to write a book, or to do programming or prove theorems. And now around the island, there's a sea, and the sea is the artificial intelligence. So that means that the sea level is always rising. So once a peak is covered by water, that means that AI has managed to do this to solve this problem, and now the human competence is not needed anymore. So this is something that can be done by AI. So here's a more schematic way of showing it. Yeah, and so the final aim is basically that the whole island is then underwater. So if it's wishful or not for us, this is the other question, but this is basically where it's all going. So the sea level is rising and rising. So, and now the question is, so how can we measure? So how clever is the AI? And I mean, we have a way how to measure the intelligence. So this is the good old intelligence quotient. So this is something that is a standardized test, which a lot of humans have already accomplished. And now there were some Chinese students, and they said, okay, so let's just measure the IQ of our artificial intelligence. And this is what they did in 2014. So these are the different artificial intelligence systems. And so here are the IQs of humans, so the average IQs. And we see that in 2014, so Google, so the Google Assistant had an IQ of 26.5. So below a 6-year-old child. So now in 2016, so you see that so now Google has nearly doubled its IQ, so just in 2 years, but still below human. So the question is, where is it all going? So now ChatGPT. So I mean, you cannot talk about AI without mentioning ChatGPT. So certainly it was not as scientific as the Chinese students did, but so here a Twitter user, so at least he works at for Amazon. He said that he did a test with ChatGPT, and he got now a general intelligence concept of 83 for ChatGPT. Yeah, so so now we come to Ray Kurzweil. So Ray Kurzweil, he is a futurologist. So he basically makes predictions of the future. So not like in novels, like a science fiction author, but he tries to sound more scientific. And he basically predicted already in 2001 in his article, The Law of Accelerated Returns, so that we achieve one human brain capability for $1,000 around the year 2023. So basically this year. So as you see, so 83 IQ 83, so it's already very close to the human intelligence, but we don't know. So how much does the hardware cost for the ChatGPT? So this is something that OpenAI doesn't disclose, but there was an announcement by Apple in 2021, so that Apple is bringing Siri, so the AI system from Apple, from a cloud-based to local on-device processing state. So that means that a mobile phone, so like here on the table, now should have the same intelligence. So probably not around 80, but around 60. So and this is the price for $1,000. So roughly it fits. So now what does Kurzweil say? So that 1 cent, so human brain capacity for 1 cent will be around 37. We achieve 1 human race capability for $1,000 around 49, and 1 cent around 59. So this is something now that using Cadence tools, you could start designing such systems, so which can achieve this kind of intelligence. Maybe just a short remark about ChatGPT. So very simplified. So what does ChatGPT do? So it basically reads a lot of text, and then it works on the probabilities. So it basically calculates. So now we have there's one word. So what is the highest probability that for the word to follow? And this is how a meaningful text is created. But so this information about the probability, it comes from the amount of the texts which were provided for learning. But what does it mean actually that there is a high probability that there is one word follows the other? That means that in the learning texts, there are a lot of facts which are repeated all the time. So when several times the same fact is repeated, so then the high probability is that ChatGPT will use exactly this fact. But how do we call this if something is repeated very, very, very often? So this is something that is just trivial. So that means that GPT is basically providing all the time some trivial facts. So that this would mean that in order to not to become irrelevant for the humans, we have to think of something which is not trivial, and only then our input, our knowledge will beat GPT. So for trivial things, GPT is the tool to use. But so our task, I mean, so all of you and me included, we need to provide something not trivial in order to compete and beat GPT. Yeah. So so some problem with AI is that so AI can become very clever, and so no question about that. So now one danger is it to to give AI problems to solve, but do it in a meaningful way. So so there's a so-called paperclip maximizer problem. So what happens if somebody tells to a very powerful AI, so just produce the paperclips. So then AI, it's now a target for AI to produce paperclips. So it starts producing paperclips, and then it realizes, okay, there are not enough resources. So now let's build more factories to produce paperclips. So then there are not enough resources on the whole planet. So then just let's create spaceships to fly to another planets in order to produce paperclips there. And so then at the end, basically the whole solar system is doing nothing but producing paperclips. So this basically illustrates that we must be very careful what we are asking for, because this is something which can be fulfilled, but not in the way that we initially intended. So it's a big problem. So how to ask the AI for something and still survive. So in order to, so if you are interested in AI topics, so here are some books so which I can recommend to read about this. So these are some philosophers who wrote these books. Yeah, so quite entertaining read. So now let's come to the machine learning in EDA. So how this is used in the electronic design automation. So why is it interesting to use artificial intelligence, or here I will talk about machine learning in EDA. So first, EDA has to deal with a huge amount of data, and it has to and a lot of problems in EDA are optimizing. So you need to find a solution which is not optimal but close enough to the to optimum, and which basically fulfills and satisfies the specification of the system. So there are a lot of algorithms available, optimization algorithms, so from the past, and therefore machine learning is just an additional algorithm, so which is also very powerful in order to enable even more optimization for the given data. And so it also must be clear that there's not one algorithm on machine learning. So there are a huge amount of different algorithms, and also there are a lot of different EDA problems. And the true art is to find which machine learning algorithm helps to solve which EDA problem. So this is something that our developers are currently working on. So just to evaluate which algorithms fits to which problem and helps to solve it. So here's just one example. So how machine learning is applied in EDA. So here, this is a problem for formal verification. So formal verification basically means that if you have a given code, so then you can mathematically prove that the code is correct. So you are not just doing it via simulation, so that you have a certain number of inputs and then you verify the outputs, but this is a mathematical proof of the correctness of your code. And there are several algorithms so which can be applied for this mathematical analysis. But the problem is that not all algorithms converge on all code. So you have to carefully select which algorithm to apply on which code. And this is something that can be automized using machine learning. So here are like these different algorithms. And now, so first approach was to do a supervised learning. So we had like 500 algorithms, 500 designs, and these 500 designs were tried out with different algorithms, and then it was verified so which algorithm converges on which code. And then a model was created, and then the model was able to predict. So if it saw a new code, so which algorithm to apply to verify. So which algorithm to apply to verify this new code. So this already works. And then the second approach was to use so-called reinforcement learning. So here no data are provided for learning, but the system was learning itself. So how to if an algorithm is converging or not, and then did some kind of self-learning, and with this using this reinforcement learning, so then the result was were even better on selecting the right algorithm. Another example of machine learning is for optimizing the regressions. So regressions, this is if you write some code and then you have a lot of tests in order to test the code if it's correct. And so if every time when you change the code, so then you have to rerun all the tests again. And so these are thousands of tests, and they are all running on servers, and we need a lot of licenses and a lot of hardware. So the aim is it possible to optimize the amount of tests, but at the same time so that the coverage, so all the states that you are checking, so that the coverage remains the same. And for this, also a machine learning algorithm was created. Oops. Yeah. So what you see here? So there are some tests written, and the tests they have different input variables, and the points that you see here. So this is always the output of the test. And so here, so in this, so in this matrix, so every you have all so every square is a valid output. And now you want to check if you have checked all the outputs. So basically, if you have at least one dot in each of the squares, or we call them bins, so then you have verified all possible outputs. Yeah. So and then you have a coverage of 100%. And this is something that so therefore you're writing the tests, you are feeding the tests with different inputs, and you try to generate as many outputs as possible. So now with machine learning, it's possible to optimize the tests, and it's possible to optimize the inputs, and then with this and then still have the same coverage or even better coverage. So you see that these dots, so they are covering more of the bins, and they use less tests and less runs. So that means that you need less licenses and you need less hardware. So then you are saving costs here. Or you can use the available hardware and the available licenses for covering even more tests. So just to increase your coverage. So now we're coming to a digital implementation. So for digital implementation, so there are also a lot of optimization problems, and one of the optimization problem is the routing problem. So how to enable, how to create optimal routing, so which connects all these millions of standard cells in a block. And so here machine learning can also help. So in the router, there is now a machine learning algorithms implemented. And what happens is that first on a given block, there are several trial routes. And then based on these trial routes, a model is created. And then there is the final detailed route. And the detailed route applies the knowledge from the previous trial routes. And then you get better results than if you immediately would run this detailed route without the previous knowledge. So basically what we see is the improvement of 12% PPA. So PPA stands for power, performance, and area. And this is the main metrics for digital design. And 12% PPA. So you remember my first slide. So what is the advantage from switching from 7 nanometer to 5 nanometer? These are 15%. So just by applying machine learning, you can basically save switching to the next node. And this is you save a lot of costs of switching to a new node just by applying better algorithms to the software. So this is very significant. Yeah, so routing is just one example, but you can use machine learning also for clock tree synthesis. You can use it for placement, You can use it for power optimization. So there are really a lot of different optimization problems during digital implementation, design flow, and so machine learning can help optimizing a lot of these problems. So Cadence provides now several of our tools with machine learning algorithms inside. And here we differentiate between machine learning inside and machine learning outside. So what's the difference? So here the blue circle, or so the blue parts of the circle. So this is where the machine learning algorithms are built inside the tools. So they are completely transparent to the user. So that means that the user doesn't even have to know that there are machine learning algorithms in the tool. So it just gets better results, but doesn't know why exactly. It's just a new algorithm which is just better than the previous algorithm. So you see that there are already several tools which have this algorithm built inside. The green one, so this is so-called machine learning outside. So machine learning outside is that the user is perfectly aware that something is happening because of the machine learning. So one example, this is already how what I showed you with the regression simulator with the Xcelium ML. So this is where the user becomes aware so that the number of runs has decreased because of the machine learning. And now we're coming to the Cerebras. So Cerebras, what it does is it optimizes the whole digital flow. So it's not only that it optimizes the results of one tool, but it looks at the whole flow. So it looks at the synthesis, it looks at the placement, at the timing optimization, the power optimization, at the clock tree synthesis, and then it tries to find a combination of the inputs and of the so how the tools are executed in order to find the best optimization for the whole design. So also what Cadence is offering is the Tensilica AI. So this is a processor IP. So it's not a software tool, it's a processor IP, so which is capable of executing AI algorithms. So now about Cerebras. So far, how is the design cycle? So we have an engineer, and the engineer starts the tools. So he starts synthesis, placement, routing, timing optimization, power optimization with different design constraints, with different library options. Then waits till the run is over, collects the results, reviews the results, and then if the results are not satisfactory, so then just tries new options and then just reruns this everything. So now the Cerebras is doing basically the same, but in automated way, and it learns from the previous runs using machine learning. So that means that the block designer is still needed, but a block designer has much more bandwidth. So now, so in the previous flows, so usually a block designer is responsible for 1, 2, 3 blocks. So here a block designer can handle 10 blocks in parallel because so all this manual process, manual cycle is not needed. It's all done by Cerebras. Of course, you still need a lot of hardware because so in Cerebras it starts a lot of runs in parallel, and of course every run needs a lot of hardware. But still, a hardware is much cheaper than a human designer. Also, hardware is more available than a human designer. So therefore, this is how a single human designer becomes more productive than before. So how does it work, the Cerebras? So it's also a reinforcement learning. So each time when a certain run or a certain scenario is created, then it starts running this certain scenario. So a scenario is so a certain inputs and certain tool flows, so certain design flows. And then it's all the time verified if the results are getting better or not. So if the results are getting better, so then this means a reward. And then this means so that the next run is using these inputs, but slightly tweaked in order to get even more reward, even better results. And then there's a machine learning model, so which always learns so what result, which inputs provided better results. So here are several scenarios are run in parallel, and then there are always metrics. And as soon as it becomes clear that a certain scenario is delivering better results, so then the run is immediately killed, and then a new run is started, but with the learning from the previous scenarios. So always the best scenario wins, and then the best scenario is tweaked again in order to get even better results. And so you can understand, so there are a lot of scenarios. They all are running in parallel. So that means that a lot of hardware is needed in order to run it. And here, of course, cloud is helping here, because cloud has basically unlimited amount of hardware. Certainly comes at a cost, but at least it's there. Yeah, so basically, Cerebras, it provides better results in terms of PPA. It provides better productivity because the block designer can handle more blocks, and it's a scalable solution. So it can run on your own server farm. It can run on the cloud. So this is something that is certainly a future for Cadence, and even more solutions. So not only digital implementation, also analog implementation, or system implementation for example, PCB, or verification. So more and more of the tools will have this enablement of machine learning, so giving more productivity to a designer. Okay, so I'm at the end of my presentation. So I hope you enjoyed it, and please, if you have some questions.
Thank you very much. It was very interesting. Do you have any questions here, Luther?
I have a few. I'm thinking if I should go back to the 3. What is coming after the 3 nanometer, for example? Do you think that the technology nodes will shrink, or will continue in one of the paths that you already shared?
So Cadence is working together with IMEC. So IMEC is an institute in Belgium, and so this is the most advanced institute in the world. So basically all the foundries, so TSMC, Samsung, Intel, they come together at IMEC, and they do so-called pre-competitive research. So they are basically finding out so what's working, what's not, and then after they find this out, so then IMEC is selling the results to the foundries, and then they work on their own technologies. So in 2019, we started participating in a government-funded project together with IMEC for development of 2 nanometers. And so in 2022, we started working with IMEC on development of 1.4 nanometers, so for 14 angstrom. So there are plans already going to 1 nanometer. But here, what will happen is, as I showed in this modern Moore slide, so there will be these three-dimensional transistors or three-dimensional structures. So basically, there's the N FET is below and the P FET is above, and this is the way how the shrinking is happening. So it's not longer just the shrink of the gate width, but it's more about so how to squeeze more transistors in one area. So then you just go in the third dimension. So the shrinking is still there. Yeah. Of course, it gets more and more expensive. So then you have to find the market for your products, but in general, it's possible. Yes.
Okay. And going back to the machine learning, you said that it's saving 12% PPA. And what is the cost on this? It's time or resources, CPU? What is the cost for reducing achieving this improvement?
Yeah, so certainly, so machine learning, it's compute intensive. So you need more hardware. So you need to do trial runs in order to create the model first, and then after you have created the model, so then you do your final run. So in order to do this trial runs, you need more hardware.
Okay, and in general for the AI, you said that the output of ChatGPT, for example, is giving the trivial answers, but sometimes when you use it, for example, for writing code or something like this, it's writing scripts or something for you. It seems like it's resolving your problem. So it gives the impression that it is intelligent. Does this mean that the answer that is being asked is trivial? Like the question that I'm asking is trivial, so ChatGPT is able to generate me a response that is seems intelligent.
Yeah, but the question, so how can it find something intelligent? So it cannot do any miracles. So it's not really thinking. It's just counting the probabilities. And so if in the past in the learning texts there were a lot of similar answers, so then it just provides you this answer.
So what will what will make it harder for the artificial intelligence? Like what are the inappropriate questions? I mean, what the AI is finding hard to resolve?
Yeah, so I mean, you can start some. I mean, if you start asking very specific questions, so where you know that very little literature is available on the market, so it could not be trained with this literature. So then you immediately start. So the answers will become very short, or it starts to say, well, I am not aware of this. So I try to ask very specific questions on electronics at some point. It couldn't really answer.
Thank you. One more thing, going back specifically into Cerebras. I've used it for a while, and it seems like it's kind of how is it determining that a certain, for example, placement, it goes through the different stages, placement, CTS, and we see that some of the runs are stopped at placement stage and the others continue through CTS. But how is it finding the best placement optimizations and when does it stop? Like, is it limited by the number of the parallel runs that you provide, or it could go forever? Like,
I must admit, I don't know the exact details, so this is something that you have to ask the expert at Cadence. Yeah, so my understanding is that so it comes. So there are certain metrics defined, and then once a metric becomes very worse at certain runs, so then the runs is immediately stopped, and then just the other runs get continued. But so exactly what are the metrics? That's something I don't know.
All right. No more questions on my side.
Okay,
thank you very much.
Any other questions?
I have two questions. One is from the introduction. You mentioned that information about design is stored in some databases. Are they only for one company, or they are spread? They are available for different companies?
Yeah, so the database for this particular tool is a proprietary database. So this is something that only Cadence tools can read.
But are there others which are more general, more common? I mean,
yeah, so
database
I don't-
about design or something like this.
I mean, so what is always available for a long time is the open access. I mean, so there's the open access database, so on which basically all analog tools are based. So not only from Cadence, but also from our competitors. I mean, this is something which is available as open source, so you can download it. So this is an open database, but of course, this kind of database, which contains not only the analog part, but also the digital design and all the information on the interconnect and on the power consumption, and so it contains much more details. So this is something which is proprietary. So it's
and the second question is about the Moore law.
Yeah.
I read somewhere someone says that maybe the end of the Moore law will be the best thing that could happen to the semiconductor industry. I think he had in mind the fact that other way of carrying the information under development. Could you comment a little bit about other carrier of information like electron spin, magnetic wall, something? They have been discussed since years, but I didn't see some practical realization.
Okay, so one thing is what I explained about more than Moore, so that all this system optimization. So this is because Moore's law is slowing down. I mean, the system optimization can go also into. So we are now. We are also doing some progress on the computer architecture. So it's not only for Neumann computer, but so now we are integrating processing units into memories, and we are working on a very different kind of memories. So not only as SRAM based, but ReRAM, FRAM, or whatever they are called, MRAM. So this is also a consequence that Moore's law is slowing down. Then, well, quantum computing. So there are a lot of money now flowing into quantum computing, and I mean, I could do another lecture about the quantum computing. So how there are many different approaches now. So it's about this cryo cooling and about photonics and about something in diamond traps and ion traps and whatever. So there are very many technologies. So how to create this quantum effect and how to do calculations with it. And so far it's not clear. So which if there will be one winner in this race, or there will be several approaches in parallel. Yeah. So this could be the next big thing. Yeah, so at least so now we see that the quantum computing is outside of the labs. So now there are commercial companies which are doing development, and they're doing it because they hope to earn money at some point with it. So, and investors, they are putting also millions into startups which are working on the quantum computing. So now it starts to become a business case, not only academic research.
Other questions? May I ask? Of course.
Is it machine learning a good idea to use in microcontrollers chips?
Yes, definitely. I mean, so that there are currently microcontrollers which have already some coprocessors for machine learning. So, for example, there is from NXP there are microcontrollers which have this accelerator for machine learning for audio processing, so that you can realize some systems with voice control, or machine learning for security cameras, for example, so that you can identify moving objects without transferring everything into the cloud, so that you are saving on the data which you don't transfer to the cloud. So this machine learning on the edge, so this is becoming more and more popular. So therefore, there will be, or there are already accelerators in microcontrollers.
Thank you.
I was just trying to check the system. Will be your presentation available for the people who attend your session?
I think it's recorded now.
No, but I mean just the presentation.
No, so I transferred it already to Gitchka, so yeah, you can use it, yes. Any questions online?
Auditory online, are there any online questions?
That was from
Okay, so thank you very much once again. And